you very much for the kind introduction and invitation to this webinar. So I'm very happy to be here. I hope you could hear me properly. Let me just share my screen. Okay, so I'm tasked to share with you our work on climate action, particularly how we use nuclear science and technology, and particularly radiation technology, particularly on corals, to deal with climate action to help achieve the UN SDG on climate action. Just to briefly introduce the Philippines, our country, it's an archipelago. It's composed of more than 7,100 islands. So 60% of our population and our communities live in the coastal municipalities. We also have a very degree of marine biodiversity. The country is even acknowledged as the center of the marine biodiversity. It is situated inside the Coral Triangle, one of the highest marine biodiversity all over the world. So therefore, our setting, we have 60% of our population living in the coastal areas, and we have a very high amount of marine biodiversity. And so the country has a very heavy responsibility to protect the natural environment, but also we are one of the most vulnerable countries against climate change and sea level rise. And so that is the main motivation of our work that I will show you this afternoon. So when we say corals, probably you imagine this type of organisms, the colorful ones and then the branching ones, the ones we see when we swim on the sea. But actually, the corals that we are looking at in our project look like these. So we call these massive types of corals, particularly of the genus Poraites. So these Poraites, if you could imagine, before they were very small, but through time, they grow bigger and bigger and bigger. And so if we take a cross section of these corals, we have something like this. So the top part of the coral, I think they have a laser pointer somewhere. Let me just find it. Laser, no. Anyway, the top part of the coral would be recent. It would be the most recent part of the coral, but as you go deeper into the coral, it would be older and older and older. And so actually, if we look at the skeletons of the corals, we have a continuous record of everything that happened in the sea and in the ocean, particularly the chemical and the physical changes and conditions in the seawater. And so these materials, we call it coral cores, are actually excellent things to study in respect to climate change and the response of the corals with the different changes in environment and climate. So we look at both modern, meaning live or living corals, modern corals, but also fossil corals, which I will show to you in the next slides. So here is how we take modern corals. So they are big living corals. We have to scuba dive to get them. And so we select a suitable coral, and by using a drill, so we take a small part of the sample. So we drill the coral, we take a small part of the coral, we call it the coral cores, and we plug the corals, the hole that we created, so that the coral can resume its growth. So the coral does not die, so we only take a small portion of its material, so it can live again. It can continue living. So the material that we get looks like these. So on the top part is the whole coral core, but we cut them into slabs, and so it's easier to analyze, and it's easier to work with, as you can see at the bottom. On the other hand, fossil corals, it's a bit easier to sample because they're already uplifted. They're already above the sea surface, and so you don't have to dive for them, but you have to spot them and you have to find them. So we could imagine that thousands of years ago, these places were submerged in seawater. So we can also take samples from those. So the first thing we do with the corals is that we analyze them using this 3D X-ray computed tomography. So the coral cores, using this technology, we could see everything that is happening along the different axes of the corals. So you could see the video that it's slicing the sample in all directions, and you could see the different features of the corals. And from those particular features, you can say something about what happened in the environment in the past and what is the response of the corals in the past in these changing environments. So as you can see here, it's slicing different axes. So you could do that with this 3D X-ray computed tomography. So particularly what we reach a resolution of 54 micrometers with each pixel. And so we could say that its corresponding time resolution in the coral is about 2.5 days. So we have a data of every 2.5 days. And if the coral is about 1 meter, a modern coral, it's about 100 years in the past. So every 2.5 days, we have a data point or an information of every 2.5 days, 100 years ago into the past. If there are fossil corals that can even reach to thousands of years in the past. So we can say something about the environment in the past and during those times. So the concept, very quickly, is that the X-ray, how dark or how light each pixel in the X-ray image corresponds or is related to the density of the coral. On the other hand, the density of the coral is related to the temperature of the seawater. At least one of the factors that control it is the temperature of the seawater, or the sea surface temperature, or SST. And so the concept is that by using the X-ray, by looking at each pixel of the X-ray, we can reconstruct, or we can know the temperature of the seawater in the past. So this is what we do. So for example, the blue line is the different gray values, how light or how dark each pixel in the X-ray image. So we take those and then we compare it to a record of daily sea surface temperature, which is available in different data packages. For example, this is from the Optimum Interrelation Sea Surface Temperature data product of NOAA, NOAA. So we can download that easily. So we compare the gray values with some database of SST that was only modern times. So we connect them like this. So we put in some connections. We call them tie lines. And then through these connections, we could create some type of calibration line or calibration equation. So as I said, the record of the sea surface temperature modern only, we don't have a record in the past. So, but at least we have the record of gray values. So using this equation, we could reconstruct the sea surface temperature during the times that there are no records available in the distant past using this technology. And so we found out that using this method, we can reconstruct sea surface temperature monthly, every month for the past 100 years or thousands of years, with a mean absolute error of 3% only. So we're very happy with that. Not only could we reconstruct again the past climate or the past temperatures, we could even reconstruct how the coral respond to them. So we have these different parameters. The first one is density. Of course, as I mentioned, the density of the skeleton of the coral is affected by whatever is happening in the sea. The second one is the linear extension rate, that is LER, or how big does the coral grow each year. So is it this big or is it this big? So we call that linear extension rate. And if we multiply those, we can get what we call the calcification rate. The calcification rate of the coral course. And so those three things says something about how the coral is, the health of the corals and how they are growing through time. When we pair that with another nuclear or science nuclear analysis, which is radiocarbon dating or uranium thorium dating, particularly for the fossil corals, we will know that, for example, our samples were 3,000 years before present or 4,000 years before present. So we could anchor all those information at a particular point in time. So, for example, 4,000 years ago, this is how hot the water was, and the corals were growing this fast, or the corals were these healthy. So that is how the information that we're getting with these samples. We could also relate them. Very, very important thing about coral bleaching. So again, healthy corals should be, so hopefully we always have healthy corals. But once the corals are stressed, particularly if the waters are too warm, so they will expel we call it zooxanthellae. These are symbiotic creatures with the corals, living symbiotically with the corals. But if the corals are stressed with too warm waters, for example, they will expel the zooxanthellae and they will become white. Instead of colloid corals, they will become bleach corals. This is coral bleaching. If the situation does not improve, then coral bleaching will lead to coral death. So the corals will die. But if the situation improves, the bleach corals can return to a healthy corals. So using those information and technology that I've shared with you, we can also see in the coral skeletons the different bleaching episodes, coral bleaching episodes in the past. So we can see them if the linear extension rate is too small, that is indicative of a coral bleaching event. So if in 1 year it didn't grow too much and the temperature was too hot, then there was a bleaching event during that time. And so we can see that in the corals as well. And so we could understand more what is the response of the corals with the changing environment. Last few slides, we also use what we call the portable XRF or handheld X-ray fluorescence spectrometry to determine the elemental components inside the coral. So as you can see in the picture, we can read the elemental concentrations along the corals per millimeter, for example. And we can tell many things based on the elements that we looked at. We can say something again about temperature, but also about rainfall, runoff, past typhoons, past sedimentation events, past floods, for example, light turbidity, ocean circulation, about nutrients. If the sea was healthy or full of nutrients, or if there was pollution. So by using XRF on the coral cores, we could also reconstruct what was happening with these different parameters using this different element as well. So last few slides to conclude by looking at coral cores, both modern and both fossil coral cores. They are excellent material to study past climate and the response of our corals in our environment. So the 3D X-ray computed tomography tells us coral growth, that is the density, linear extension rate, calcification rate, plus past climate information, that is sea surface temperature, for example, coral bleaching events, and through carbon-14 and uranium-thorium dating, we can tell the age of the corals when all of these events happened in the past. And by using XRF, we could get elemental concentrations that can tell us like rainfall, runoff, turbidity, sedimentation, past typhoons, nutrients, redox conditions, pollutions, and other things that has happened in our environment in the past. And all this information can be used to better understand the response of our natural environment to climate change. And that information could help us, our governments and our agencies to craft policies to better prepare, particularly to reduce the risk and to mitigate the impacts of possible climate change that can happen in our areas in the future. So that is my last slide. So this is our office. If you have a chance to visit us, please do so. And please tell me. So thank you very much for your attention.